Hello everyone, welcome back to my channel. In this video I'll be explaining you how to analyze a continuous beam with the overhang using slope deflection method. Okay, so just read the question. We have analyze the continuous beam shown in the figure using slope deflection method. Also draw shear force diagram and bending moment diagram when EI, the flexural rigidity, is constant. So you can observe you have a continuous beam given. You know what's a continuous beam, right? Continuous beam means it's a beam which is resting on more than two supports. Right. Now in this beam, for the part AB you have a eccentric point load, and for the part BC you have a UDL, and the CD part is the overhanging portion. Okay. So always remember, in slope deflection method the first step will be writing the fixed end moments, okay, also called FEM. So for fixed end moments, let's start writing. See here, we have totally two complete spans, so you will be getting 4 fixed end moments and 1 moment for the overhanging portion. Okay, how do you get 2 moments for one span? One moment will be in the clock direction and the other moment will be in the anti-clock direction. So let's start off with M bar AB. So M bar AB is the anti-clock moment which is coming from A to B. So it is formula is minus W AB square by L square. Why? Because here in the part AB you have a eccentric point load. Okay, so the formula is minus W AB square by L square, where W is 100, A is 4 and B is 2. L is the span of AB. So just substitute all the values, you will be getting minus 44.44 kilonewton meter. Similarly, M bar BA. So it's the moment from B to A, which is the clock moment, and the formula is W A square B by L square. Same, W is again 100, A is 4, B is 2 and span is 6. So substitute the values, you will be getting as 88.88 kilonewton meter. Similarly, let's do M bar BC. M bar BC, here you have a UDL acting on the span BC. So for UDL, the anti-clock moment is given by the formula minus WL square by 12. So it's minus 20 into 5 square by 12, which is minus 41.67 kilonewton meter. Similarly, M bar CV, it will be a clock moment from C to B and it's given by the formula WL square by 12. It's 20 into 5 square by 12, which is 41.67 kilonewton meter. So next is M bar CD. So it's the moment from C to D, which is an anti-clockwise moment. So it is load into the perpendicular distance. So it's 20 into 1.5, which is minus 30 kilonewton meter. This is how you need to complete the first step, which is writing the fixed end moments. Next, our step 2 will be writing the slope deflection equations. So for how many we have 4 moments for 2 spans, so we will be getting 4 slope deflection equations. So let's start off. The first slope deflection equation is for MAB. So MAB is equals to M bar AB plus 2 EI by L into 2 theta A plus theta B minus 3 delta by L. This is the formula. Here, remember a shortcut we are doing for AB. So A is coming first, B is coming second. So here, the first alphabet whichever is coming, that will have 2 times theta. Okay. So here AB means 2 times theta A plus theta B minus 3 delta by L. The other thing will be common. Here end A is fixed, right? So at a fixed support you don't have slope. So theta A is equal to 0, and delta stands for sinking. Here nothing in the problem is related to sinking. So there is no sinking at all. So delta equal to 0. So now let's substitute. MAB equal to, what is M bar AB from step 1? Minus 44.44 plus 2 EI by L. What is span of AB? 6 by 6 into, however this became 0, this also became 0. So you're left with theta B. So finally what is MAB equal to? Minus 44.44 plus, this is 2 1s 2 3s, EI by 3 into theta B. That's our equation number 1. Similarly, let's write for MBA. So the formula is M bar BA plus 2 EI by L into, as I've told you, whichever alphabet is coming first, that will have 2 times. So 2 theta B plus theta A minus 3 delta by L. Similarly, same, theta A is 0. Why? Because end A is fixed. Delta is 0. Why? Because nothing related to sinking is given. So MBA equal to M bar BA from our step 1 was 88.88. So 88.88 plus 2 EI by L means span of AB or BA is the same, 6 into 2 theta B. This and this became 0. So just simplify the equation, you will be left with MBA equal to 88.88 plus, this is 2 1s 2 3s. So this is 2 into 2, this becomes 4. Okay, 2 1s 2 3s Okay, sorry, this is 2 only. I'm sorry, I did correct only. So it's 2 EI by 3 into theta B. Next, let's go for third slope deflection equation, which is MBC. M bar BC plus 2 EI by L into 2 theta B plus theta C minus 3 delta by L is the formula. So here B and C slopes both will exist. Why? Because if you observe in the continuous beam, our B is an intermediate support, C is also an intermediate support, okay, and they are not fixed, so hence theta B will exist as well as theta C will exist, okay. So only nothing related to sinking is given, that's why only delta will become 0, other all will exist, so only I made delta equal to 0. So let's substitute the value of M bar BC, which came from step 1, which is minus 41.67 plus 2 EI by L is 5, means the span of BC is 5 into 2 theta B plus theta C. The term related to delta became 0. So M bar BC will be minus 41.67 plus, this is 2 into 2, 4 by 5 EI theta B plus 2 by 5 EI theta C. That's equation number 3. Similarly, let's write for MCB, the last slope deflection equation. The formula is M bar CB plus 2 EI by L into 2 times theta C, the first alphabet whichever is coming, into plus theta B minus 3 delta by L. Similarly, theta B, theta C both will exist, only delta will be equal to 0. So MCB equal to, M bar CB is from step 1, the fixed moment 41.67 plus 2 EI by 5 into 2 theta C plus theta B. So finally MCB will be 41.67 plus 2 into 2 by 5 in EI into theta B is 2 by 5 EI theta B plus this is 2 into 2, 4 by 5 EI theta C. Okay, that's equation number 4. And last slope deflection equation, directly we wrote MCD equal to M bar CD equal to minus 30. Why? Because D is not a support. If D is a support, then we should write slope deflection equation for MCD also, like M bar CD plus 2EI by L and so on, like that we should write. But D is not a support, it's just an overhanging part, so you can't take it as a support and start writing the slope deflection equation. So here MCD will be directly M bar CD, which we calculated, which is minus 20 into 1.5 minus 30. So we are done with step 2, writing the slope deflection equations. Next comes our step 3, which is the main important step here in slope deflection method, which is equilibrium condition. Now see here how to apply the equilibrium conditions. Now see here, in this overhanging beam, B is the intermediate support. Now if this support should be in equilibrium, means the moment which is going towards left from B plus the moment which is going towards right side from B should be equal to 0. Means MBA plus MBC must be equal to 0. Similarly, at support C also, from C to B there is a moment going, which is our MCB. Similarly, from C to D also there is a moment going. Even though CD part is overhanging, some moment is going towards C to D. Okay, or else you can see this 20 into 1.5 moment is coming towards C. So C is also getting affected. So at C also you should apply the equilibrium condition. So what you should do is you should apply equilibrium conditions at the intermediate supports. Okay, and sometimes if suppose this overhang part is not there, so our C is a simple support, now it's not fixed, so at that time another equilibrium condition will be MCB equal to 0 directly, like that you have to do. Now in our problem, the first equilibrium condition will be at joint B and second equilibrium condition will be at joint C. Yeah, that's what I've written here. See, for the joint B to be in equilibrium, MBA plus MBC equal to 0. So MBA I gave it with equation number 2 and MBC I represented with equation number 3. Just add both the equations and simplify. You'll be left with 47.2 plus 22 by 15 EI theta B plus 2 by 5 EI theta C equal to 0. Take it as equation number 6. Let's continue the numbering. Similarly, as I've told you, at C also we should take the equilibrium condition. Moments from moving towards left of C plus moment which is moving towards right of C should be added and made equal to 0. So MCB plus MCD equal to 0. MCB was our equation number 4. Here it is. So just take that equation plus MCD is equation number 5. Just add both the equations and simplify. You'll be getting 11.67 plus 2 by 5 EI theta B plus 4 by 5 EI theta C. Take it as equation number 7. Now observe equation 6 and 7. What are the unknowns here? Theta B and theta C, or rather EI theta B and EI theta C. We have two unknowns. We have two equations, 6 and 7. So just solve equation 6 and 7. Okay, just have take your scientific calculator, go to the mode setup, take the equation I think it will be number 5. Take the equation format and just substitute the values. You'll get the values of ei theta b and ei theta c. So after solving, I got ei theta b as minus 32.67 and ei theta c as plus 1.75. Now I am ready with the slopes. So what should I do now? I should calculate the final moments. That will be our step number 4. So how you'll get the final moments? You have to start substituting this ei theta b and ei theta c right from equation 1, equation 2 and equation 3 and equation 4. However, equation 5 is already minus 30, we know. So substitute the values of slopes right from equation 1 to equation number 4. So as I've told you, our step number 4 will be final moments. So substituting the values of ei theta b and ei theta c in equations 1 to 4. So just substitute, you'll be getting MAB as minus 55.33, MBA as 67.1, MBC as minus 67.1, MCB as plus 30 kilonewton meter, and similarly MCD already we know 20 into 1.5, which is minus 30 kilonewton meter. So see, observe, as I've told you, we applied a equilibrium condition at joint B, right? What did you write? MBA plus MBC 0. So see here, this is plus 67.1 and this is minus 67.1. Just add them, it is 0. So we can have a cross check here. Similarly, we wrote another equilibrium condition at joint C, right? MCB plus MCD equal to 0. So you have plus 30 and minus 30. Add them, it is 0. Correct? You have another cross check here also. So like this, you have to check. After getting the final moments, you have to check whether you did it correct or not. Here itself you will understand. If you're not getting same answers, means then you made a mistake somewhere in the calculation. Next, in advance I'm calculating the bending moment under the load AB. If you remember, in our question we had for the part AB we had a UDL, right? So maximum bending moment will occur under this load 100 kilonewton, and the bending moment diagram for this will look like a triangle, and that triangle will have a height of WAB by L. The ordinate is given by the formula WAB by L. So W is 100, A is 4, B is 2. Just divide, you get 133.33. Similarly, bending moment in the span BC. So BC part we have a UDL, and the bending moment diagram for the UDL will be like a parabola. So the height of the parabola is given by the formula WL square by 8. So it's 20 into 5 square by 8. So it is 20 into 5 square by 8, which is 62.5 kilonewton meter. Okay, so that we can finish off the bending moment diagram. So I'll explain you first the bending moment diagram, then I'll explain you support reactions. So see here, this is our bending moment diagram. See up to this part only. So first draw a line. We got MAB, right? How much was our MAB equal to? It was minus 55.33. So I have drawn minus 55.33. Next, and remember one sign convention here. We will follow the sign convention like if you take this as your beam or whatever span you are drawing, just remember this sign convention for drawing a bending moment diagram. Okay, if for the moments when you are doing from left to right, like for example, if this is like your A and B, we have two moments, right? MAB and MBA, correct? So if you get MAB means what? From A to B. If you get your MAB negative value, then draw the bending moment diagram above the span. If you get MAB positive, then draw it below the span. Similarly, MBA means what? From B to A, from right to left. If you get MBA positive, draw above the line. If you get MBA negative, draw below the line. Remember this sign convention. Okay, now I got MAB negative, so I should draw above the line. So I have drawn 55.33. Similarly, let me check for what was MBA. What did we get MBA as? 67.1. I got positive answer. So again draw above the line. So 67 point I have drawn. 67.1. Similarly, let's see for MBC and MCB. MBC also stands at the same place. MCB 30. What is MCB? From C to B. I got positive. So according to the sign convention, I got positive means I should draw upward. So I have drawn 30 upward. Now what you do is just this line, and this line. You erect them, then you start joining them from 55.33 to 67.1, from 67.1 to 30, and from here. So your bending moment diagram with respect to final moments will be ready. Now we should complete the bending moment diagram with respect to given loading. We have already calculated the ordinate under the load 100 kN, correct? How much did we get the answer? 133.33, WAB by L formula. Erect 133.33. Then we have calculated bending moment in the span BC. Ordinate formula was WL square by 8. We got 62.5, erect 62.5. Now just draw the bending moment diagram, a triangle like this, then draw parabola like this. So whatever is left over, this all got removed. The net bending moment in the net, now this is called as the net bending moment diagram. So see here, whatever is the empty part, that is all deleted. So you are left only with this part, the parts which I have shown with a line. So you have to draw like that and show that's the leftover thing. Okay, so this is negative, this is positive, this is negative, this is positive, and this is also negative. Like this you have to finish off the bending moment diagram. Let's continue. Now step 5 is support reactions. I am calculating support reactions in order to draw the shear force diagram. Okay, I'll consider the span AB first. You do it separately in order to avoid confusion. So span AB I have drawn separately. This is RA, this is RB, 100 kN, 4 meter, 2 meter. I have got MAB value as 55.33. I have shown anti-clock. Remember here MAB got minus 55.33 means the magnitude of MAB is 55.33 in anti-clock direction. So instead of putting a minus, I showed the direction as anti-clock. So when you are substituting for MAB, you need not put minus again. Minus here it is showing the direction only. It's not the magnitude. Similarly, MBA was 67.1 clock direction I have shown. Now let's start. RA plus RB is equal to total downward load, which is 100. I am taking moments about A. So when you are taking moments about A, RB will go to in anti-clock direction. So minus RB into total span is 6 plus 100 will go in clock direction towards A plus 100 into 4. This is clock direction plus 67.1 minus 55.33 equal to 0. That's what I am repeating here. Most of the people when they are writing here, they will write minus of minus 55.33. That's completely wrong. 55.33 represents moment in anti-clock direction already. There MAB equal to minus 55.33 means MAB is acting in anti-clock direction. I have shown here already anti-clock direction, so I need not substitute again a minus. Directly I am giving. So after substitution, get RB as 68.6 kN. Then what will be RA? 100 minus this value, 31.37. Similarly, let's consider span BC. This is RB, RC, UDL 20 and 5. Again, BC was minus 67.1 means 67.1 in anti-clock, and I got MCB as 30. Most of the people when doing overhang for calculation of support reactions, they get confused. Here nothing else to confuse. Why? Because already here there is an overhang portion, you remember, 20 into 1.5. That moment I am taking at C itself. I am not neglecting that moment. So directly I am considering that 30 here only. 20 into 1.5 minus 30 I got, right? That I am giving it here only. So you need not worry about overhang portion. So RB plus RC equal to 20 into 5, 100. Then taking moments about B. So minus RC into 5 plus 20 into 5 into 5 by 2. Why? Because we assume the UDL to be like a rectangle. So total load is 20 into 5. Centroidal distance will be half of the rectangle into 5 by 2 plus 30 clock direction towards B, 67.1 anti-clock direction minus 67.1 equal to 0. So finally you get RC as 42.58. Once you get RC, calculate RB, which is 100 minus this 42.58, you will be getting 57.52. Now for the span AB I am ready with RA and RB. For the span BC I am ready with RB and RC. I can start off the shear force diagram. I'll follow the sign convention of RUN, right side upward negative. So if I consider any section, I consider this sign convention, right side upward negative and left side upward positive. Okay, right now. Just remember these values. RA is 31.37, RB is 68.6. Now, when I am considering the span AB, RA I got 37.37. Okay, according to this sign convention, right side upward should be negative. Okay, and left side upward should be positive. So how much was my RA? 31.37. So RA is standing left side of my section. So it should be positive. So I have drawn upward. And I told RB right side upward negative, right? RB I got positive value. But it is moving upward. But it is towards right side of my section. So draw it negative. So I have drawn downward. Okay, since it's a point load, this 31 will continue till here. Here you have 100 acting. So 31 minus 100 will be 68. Like this you will finish off. Next, consider this bending moment, this shear force diagram for the span BC. So I got RB as 57.42, same sign convention, left side upward positive. RC I got 42.58, same sign convention, right side upward negative. So just join like this. So you have a maximum bending moment occurring here. So there are at least there you try to make it 0, the shear force. So like this you continue. Then we had a 20 kilonewton acting here, right? So it is right side upward is negative, right? Means if you consider the part CD, D is right side. So right side upward positive means right side downward will be, sorry, right side upward negative means right side downward will be positive. RUN, right? Right side upward negative. So if I get like this, it's negative, but our 20 was acting downward, so it's positive. So complete the shear force diagram like this. So like this you have to finish up the entire diagram. This is the given beam, this is the net bending moment diagram in kilonewton meter, this is the shear force diagram in kilonewton. Like this you have to solve the entire problem. Okay, hope you understood this video, and thank you.